Hello dear students, today's topic of discussion in ray optics is refraction. The basic definition of refraction that we have studied in the way lower classes also, the bending of light when medium changes. Bending of light, and what is the cause? Cause of the change in speed of light. And why that changes? Because of the change in permittivity and permeability, that we know that C is equal to 1 upon square root of mu into epsilon. I am writing naught because C is the speed of light in vacuum or air, we can say. So these two, permeability and permittivity, this changes from medium to medium, and due to that speed of light changes. Moreover, one very basic fundamental concept is, for wave, the density of medium is being decided by refractive index. Here we don't talk about the particle density. It's not mass upon volume. It is the refractive index that decides whether the medium is denser or rare. In other words, we can say if speed of wave is greater, that means the medium is rarer. If the speed of wave is lesser, that medium is denser. So it starts with the application point of this refraction, and the very first point is the Snell's law. See, what is Snell's law? The application point, and the point is mu sine theta is constant. In school physics, like if we are not discussing the competitive exam like NEET or JEE mains or IIT, in general, in school, in examination, we write that mu is sin I by sin R. But let me tell you, that is one of the form of Snell's law. That's not the proper Snell's law. What exactly is Snell's law? See, I'm describing it for you. Suppose this is a light ray. This is the light ray, okay? And on one light ray, you can see here, on one light ray, mu, refractive index, and sine theta. Theta here is angle of incidence or angle with the normal. We can tell theta is, what is theta? Theta is angle with normal. Angle with normal. Nice. So on one ray, these two product remains constant. So if we are saying that at one the refractive index is mu1 and the angle of incidence, angle with normal, is theta 1. So the product is mu1 sine theta 1. And at 2, if the refractive index is mu2 and angle here is theta 2, if theta 2 we are writing here, we have to write mu2 here. This, not this. So here we are writing mu2, so mu2 into sine theta 2, these two product, that needs to be constant. On that basis, we can see one question on this basis. See, this is a slab. When you will have a look on the refractive index of that slab, that refractive index is A minus By. A minus By. Here A and B given here are the positive constants, and Y is the Y variable. We can say the vertical variable. Thickness is T, and we can assume that slab is having enough sufficient thickness. Now question is asking us, calculate the maximum displacement of the ray inside the slab. Maximum displacement. See what will happen when we will consider mu, A minus By. As the light ray will enter the slab, gradually Y will keep on increasing. If Y is increasing, By will increase. And if By is increasing, that is being subtracted from A minus By, that is mu, will decrease. So if mu is, this is increasing, so A minus By is decreasing. So what if mu is decreasing? Mu is decreasing, so that medium is become rarer. Higher mu is denser, lesser mu is rarer. So mu is rarer, light will go away from the normal, and at one point it will do the U-turn away from the normal. You will apparently see the light ray covering a curved path that we often see in a medium of variable refractive index. Constant refractive index, light ray is constant. in variable refractive index, although it travels in a straight line, but the entire path appears to be curved path. So this is taking a U-turn from here. At the U-turn point, the angle with normal must be 90 degree. Now say this point is 1 and this point is 2. So these 2 points lie on the same ray. Then we can use Snell's law as mu1 sine 60 degree is equal to mu2. Let's say this displacement is y max inside the slab. So what you will write for mu? A minus b y max into angle we can see here is 90 degree and sine 90 degree is 1. So the equation will be mu1, and mu1 is what? mu1 is air. So we can write it as 1 sine 60 is root 3 by 2 is equal to a minus by max, and from here we can calculate y max. So this was a question of variable refractive index as well as to understand what exactly is Snell's law. Mu sine theta, the product remains constant for 2 points on one light ray. Moreover, you can see, suppose refractive index are equal. A light ray is entering a slab, being refracted, again refracted, and getting out of the slab. So at initial and final point, the mediums were air. So mu was same. So if initial and final mu, say mu1 and mu2, these two, if they remain same, obviously theta 1, theta 2, they will also remain same. So we can say the angle of incident and angle of refracted are equal. Hence the incident and the emergent light rays are parallel. This is what happens in the refraction of glass slab. So we have done with the basic definition of refraction. See, there are many theories, many applications, many questions, but as far as NEET is concerned, I can tell you 2 tricks to that. In refraction, only basic fundamentally 2 formulae are going to be used. The first one, if you see in a question, the question is of refraction and incidence angle is given. I'm not talking about rest of the thing what is required, but if the incidence angle is given or required, the question is certainly using the Snell's law. But if you see a question of refraction with no incidence angle, then in that we use the spherical surface refraction formula, that is mu2 by v, mu1 by u, mu2 minus mu1 by r. That we will discuss later topic. So we are starting from refraction from a plane surface, and in this we are just viewing a refraction from a glass slab. So refraction from a glass slab, we can see the ray diagram here. This is the object, actual object, and this is the glass slab here. Observer is all obviously here. We can say eyes are here for observer. Light is going, being incident on point 1, then it is refracted from here, and then again being incident on point 2. So there are 2 refraction, 1 and 2. How to decide refractive index for refraction? You just get my point. The refractive index is not defined by the actual location of object or image. Rather, it is being defined according to the incident and the refracted ray. For one, you can say the incident ray is in this medium. This I am saying as air. It means for one, the refractive index of object, it means refractive index of incident ray, and that is mu equal to 1 air. So for first refraction, object is in air. Okay, so from air to this medium, say the refractive index is mu, light is going to the denser medium will deviate a little towards the normal. So this light, in between the light inside the slab, this is appear to come from here I1. So what is the object for first refraction? I1. And in case of successive refraction, the image of first is object for the second. I1 is the image for first, and that will act like object for the second. So for 2, I1 is the object, and then this ray, say at 2, light rays being incident and medium glass slab, that is mu. So for this ray, although this ray is coming from I1, but if I will ask you what is the medium for this I1, you cannot say I1 is in air. You cannot say I1 is in rare medium, because see, this ray is in denser medium, so refractive index of I1 is mu, not air. So for object, refractive index of object means refractive index of the incident ray. Refractive index of image is the refractive index of refracted ray. So eventually we see that object has been shifted to I. So do remember the shift formula in glass slab, that is T thickness into 1 minus 1 by mu, and this is always towards the denser medium. So you can check here object, where is the denser medium, in the left of the object or in the right of the object? Obviously in the right of the object, as there was the glass slab present. So this object is shifted towards this. This is the shifting, and this is the formula. Basically what kind of element, device, optical device is the glass slab? This is shifting device, shifting the object from its position where towards the denser one. If glass slab is denser, towards it. If glass slab is not denser, then away from it. Now we will see a numerical on this basis. See, this is the concave mirror with focal length given. Okay, focal length is given. There is an object at a distance 21 centimeter, and you can see a glass slab in between. So what kind of optical instrument is the glass slab? The shifting device. So what it will do? It will shift. It will shift towards the denser one. This is air, this is glass slab, so this object will apparently shift it towards right. So we will first calculate the shift, that is equal to T, that is 3, into 1 minus 1 by mu, that is 1 minus 1 by 2 by 3 we can say, because mu is given as 3 by 2, and that will be 1 centimeter. So where is this object shifting? This is shifting towards glass slab. Here is the actual object, and not actual, I mean to say actual object as compared to the concave mirror. And this shifting of 1 centimeter is actually making the object distance as 20 centimeter from the pole of the concave mirror, right? Now what is the focal length of the concave mirror? Focal length of the concave mirror is f. So what is the radius of curvature? 2f, 20 centimeter. It means for concave mirror, the object is at a distance of 20 centimeter, which is obviously the radius of curvature, means the object is at center of curvature, so its image will be formed on itself. So the next important topic in refraction for NEET is TIR, total internal reflection. What is the total internal reflection? What are the basic cases? Let's see. First, for TIR to have denser medium object. So object in denser medium. Second, I incidence angle greater than or equal to the critical angle, and sin C, sine of that critical angle, is mu rare by mu denser, and if the rarer medium is air, mu r is 1, sin C is 1 by mu. You can see from here, see, this is the object, and many lights are coming off that object. So TIR is not for all the rays of one object. This is for one ray, like many rays are there from one certain object. So some of the rays can undergo TIR, some of the rays can go undeviated. So these rays are going undeviated. This ray is at, you can see the refraction angle is 90. When the refraction angle is 90, then only the incidence angle is called the critical angle. And after that, the rays are coming in the medium back known as TIR. So these are the basic theory of TIR, but there are certain numerical applications of TIR. You must be aware of all of them. They are very important. Do go through them, and we are starting from the first one, which is called circle of illuminance. You can see here, this is an object, source of light, at a depth of h in a denser medium. The second medium you can see is air. So light rays are going from here, and at this point you can see the R is 90 and the angle is critical. After that, if an observer is in air, he can see this object through refracted ray. So after this point, refracted ray are not going in that medium, so this object can be seen from a circular area whose radius is R, and that circle is called circle of illuminance. How to calculate the radius? Very easy one. Use the trigonometry. Sin C is perpendicular r upon base h. Tan C is r upon h, and tan C is sin C by cos C. So sin C, you know 1 by mu. Cos C is 1 minus sin square C under root, and sin C is 1 by mu. So in this way, we will calculate the radius as h upon under root mu square minus 1. You can directly memorize this radius of circle of illuminance. And in this, do remember, mu means mu denser upon mu rare. So if rarer medium is not air, write mu as mu d by mu r. Okay? Okay, the next and very important application of TIR is deviation in TIR. See, deviation means what? A light ray is going along some path and it either refracted or reflected. So it leaves its path. So it is getting deviated. So in that deviation, one thing conceptually you have to observe that this light ray is going. Okay? This is critical angle, say. This angle is critical angle. At critical angle, two things happen. First, the ray is going at r equal to 90, and the second, the ray is getting totally internally reflected. These are the two things. When the ray actually approaches C, the critical angle, the r is 90. As soon as the ray crosses C, then it is TIR. So there are two kind of deviations almost at the same angle C. You can see C. There is two graph of deviation. First, I will try to calculate the deviation here. The light ray is going like this. This is C, this is also C. And this is the deviation, that is obviously 90 minus C pi by 2 minus C is the deviation. So pi by 2 minus C is the deviation. This graph is this. Why it is curved? Because these two rays are of different medium, refracted. Refraction angle is 90. But as soon as the light has just crossed the C critical angle, this is the TIR, and this TIR, it is actually reflection in the denser medium, and this deviation is, you can see, pi minus 2C. This is pi minus 2C. This deviation diagrammatically also you can see is greater than this. So this deviation at C only increases from pi by 2 minus C to pi minus 2C, and then deviation is decreasing. Put here C equal to pi by 2, and what you will get is the zero deviation. So this is a proper graph of deviation in TIR. Question might ask you the entire graph or graph for a certain segment. Suppose they are asking you from 0 to C, so this one is the option. From C to pi by 2, that one is the option. So for a certain segment or for the entire TIR, the deviation could be asked in NEET. Now moving to the next application of TIR. See, at times the question asks you TIR of all the rays. There is a tube, there is a device, there is an instrument. Light is entering in that instrument, and the question asks you for the condition that whatever light has entered, all will come out. So the TIR is there for all they are not getting refracted. In such case, I am showing one example. This is a bent tube, you can see. Refractive index is mu, radius of the curved path is r, and the width is d. At point A, some rays are entering it, and these all entered rays leaving it's coming out of point B. So what condition should be there? How to think for this? Just go for the extreme rays. Like here, extreme rays, you can see at this point rays are going like this, at this point rays are going like this, and draw the normal at these 2 points. Do remember, normal will always pass through the center. So with these dotted lines are the normal. These two lights are at the extreme end, and you can check whose incidence angle is smaller. Incidence angle is smaller for this. This is the smaller incidence angle, say angle theta. Now, if the smaller angle, this is obviously greater than this, if the smaller angle is less than the smaller angle is, we are doing TIR, is greater than critical angle. This is inequality. If the smaller angle is greater than critical angle, obviously rest all the angle of incidence will be greater than the critical angle. So go for the search of smaller angle in such cases. So we can now write sin theta is greater than equal to what? Sin C. And sine theta from this diagram you can see is r upon r plus d. Don't forget the width was d. Assume it to be uniform everywhere. And sine c is mu r by mu d, and the rarer medium is not given, means obviously it's air. So 1 by mu. This is the condition, and from this condition anything could be asked, either the ratio of d by r or r itself. If d is given, suppose d is given n times r, the value of n, anything can be there in the 4 options. So this is the condition. You have to look for the smaller angle, and that smaller angle must be the greater than critical angle if the entire all the rays needs to be undergo TIR. The next application is optical fiber case. You know, for the data transfer, we are using this for the transmission of data. This is the optical fiber. In this, the actual condition is required at what angle that information, that the ray should enter the optical fiber. This I is actually required in such questions. So see, if this is going inside, obviously refracted from air to that medium, say the refractive index is mu. But what we need for the greater efficiency of the transfer of data, we want this to be TIR. No signal is going outside. It means this incidence must be in denser medium, then only TIR can be achieved. And this is in denser medium, means mu should be greater than that. So what we do is called cladding. There is a cladding over here, and that cladding has a refractive index of mu dash, which is less than mu. Since mu is greater, obviously TIR will be there. So how to calculate this? Can you see this right angle triangle here? Here you can write r plus critical angle is pi by 2. Okay, and at point O, if you can see, I have told you earlier also, if in a question of refraction you find incidence angle is there or incidence angle is required, that question will involve Snell's law. So we will use Snell's law at point A. Sin I is equal to mu sin r, and that sin r can be calculated from here, which is pi by 2 minus c. So you can write mu sin r is pi by 2 minus a is cos c, and that cos c is, you can write square root of 1 minus sin square c. Don't forget, here sin c is not 1 by mu. Here sin c is mu dash by mu. And when you will put it here, mu dash by mu, what you will find is I is equal to sin inverse square root of mu square minus mu dash square is the incidence angle. So this is a question based on optical fiber, quite frequent with the topic TIR. The third one is, and the trending question on TIR is the TIR through the prism. See, this is a prism. You can see a very ideal shape of prism we call equilateral prism, and you can see an incident angle there. This incidence angle is being refracted, and then we see 3 kind of rays, 1, 2, 3. One is going out, emergent. One is going along the surface, that's called grazing emergence, and the third obviously is TIR. First, let me tell you why I have chosen 90 degree. In prism question, many things can be required asked in a question, but if the incidence angle on the first surface is not given, you can generalize it to be 90 degree or almost 90 degree, because if something happens at 90 degree, it will happen at all the angles. So here if TIR is taking place at 90 or almost 90, then you can expect that TIR at approximately all the angles. So see, if this is 90 degree, can you see this C? Yes, you can. And from the property of prism, we know that A is this C plus this here. This is R2, or you can say R or R2, this. Now the rays 1, 2 and 3 will depend upon the value of R2. So for ray 1, students, for ray 1, you need this R2, which is basically the incidence angle at the second surface, to be less than critical angle. And if R2 is less than C, so C plus less than C is A less than 2C, for which ray? 1. Similarly, if A is equal to 2C, which ray? 2. If it will be C, obviously it will be 90, and for 90 the second ray you can see. But if you want TIR, let me write TIR here. For TIR, the third ray, A, the prism angle must be greater than 2C. A must be greater than 2C. Also can be written as A by 2 greater than C, or sine A by 2. Here you can see sine A by 2 is greater than sine C, and sine C is 1 by mu. So mu greater than cosec A by 2. So if refractive index is there, this you can use for TIR, or if you have to compare A with C, A greater than 2C. So these are the basic question topics. Must revise them on the basis of TIR. Now the next topic of refraction is the normal shift. Important one as far as the question point is concerned. See, for normal shift, first case we have assumed that the object is in denser medium. See the ray diagram, this is the object. Obviously, this is point object, rays will emerge in the spherical locus. These are going in all directions. At this point, you can see this is going away from the normal in the rare medium. Okay, so if eyes are here for any observer, what will he observe? He will observe the rays are coming from this point. So clearly this is the shifting, which we denote by delta. In this case, when object is in denser medium, you can easily see the apparent depth that AI is less than the real depth that was AO. So what is the relation? Relation is AI is AO by mu, or the apparent depth is the real depth divided by mu. Okay, so this is the value of this apparent depth AI. So what is the shifting? Shifting is obviously the total minus AI, the real minus the apparent, and that shift is d real. D real means the real depth into 1 minus 1 by mu is the shift, and this is the apparent depth. So we will see one question on this basis. See, this is a liquid. You can see the refractive index. This is a variable one, 1 plus y by h. So as the y will keep on increasing, the mu refractive index will increase, so medium is getting denser and denser, non-homogeneous liquid. So what is the depth of, what is the shift in the base? The question asks, what is the apparent depth of the base first that is required? Since this is a non-uniform refractive index question, we will use integral differential physics. The solving process will be different, but the formula will be intact. That same formula, this d apparent is d real by mu. See how to solve this. Consider a very small layer at a depth y. Now this small layer, which is obviously dy, is our object now, and for dy we are going to calculate the shift. So what is the d apparent, or we can say the apparent depth for dy? That is obviously dy upon the refractive index. Dy is the real differential small d real, so divided by mu, and value of mu we can put here as 1 plus y by h. So this is the apparent depth of dy only. So there are many such dy in the liquid. So the total apparent depth is integration of this from 0 to h, which is ln 1 plus y by h into h. From where to where? 0 to h. Put these values, you will get h ln 2 as the total apparent depth. But question is asking you for the shift. What was the actual real depth? H. What is apparent? H ln 2. So this is h 1 minus ln 2. This is the shift. Okay. Now the second one is object in rare medium. See this diagram. This is the object in rare medium. ray diagram, it's coming here. As the ray is going from rare to denser, it will bend slightly towards the normal. If eyes of an observer are here, this rays is appear to come from this point I. Okay? So you can see here AI, that is the apparent depth, is greater than the real depth. So the relation is AI apparent is mu times real. And this is the shifting from here to here. This is shift that we denote by delta, which is equal to apparent minus real, mu minus 1 into real depth. Mu, suppose we say real depth is t, so this is mu minus 1 into t. So when object was in denser medium, it was t into 1 minus 1 by mu. When object is in rarer medium, this is t into mu minus 1. Let's see a question on this. See, in this arrangement, you can see water is here, and water, obviously the refractive index would be 4 upon 3. There is a fish here diving upwards with the velocity 3 meters per second, and it observes a kingfisher. So I can write velocity of kingfisher with respect to fish is 9 meters per second. Okay? That diving upward fish observes a kingfisher coming downward with a speed of 9 meters per second. So question is asking us actual velocity of kingfisher you have to find out. Okay? See, the very first concept, whenever in ray optics the question is regarding speed and velocity, what we do, we generally relate the displacements for what the velocities have been given. So velocity is given there for fish, for relative velocity means the apparent shift of kingfisher. So let's see, this is kingfisher and this is the fish. This is the interface. From the interface of water and air, kingfisher is at a distance, actual distance of y, and fish is at actual depth of x. Okay? Kingfisher, actual I'm talking about, not with respect to fish. Actual height of kingfisher from the surface is y, and actual depth of fish from the surface is, say, x. So if this is actually at y, at what its image will be formed? It will be formed at mu I. So to fish, it is not at y, rather it is at mu I. So the total gap between the, you can say, apparent position of kingfisher and the actual position of fish, say h, is x plus mu I. So this is the displacement relation. Now, what is dh by dt? dh by dt is dx by dt plus mu dy by dt. This is the trick to solve velocity questions in ray optics. First write the displacement relation, then the constant one, differentiate with respect to time to get velocity. dh by dt, this h is the height between apparent position of kingfisher and fish. So the relative velocity dh by dt is 9 meters per second. dx by dt is 3 plus mu is 4 by 3. And what was y? Y was the actual height of kingfisher. So dy by dt is the actual velocity of kingfisher, and this is required in this question. So here we can calculate VKF, the actual velocity, as 9 minus 3, 6 into 3, 18 by 4. That is 4.5 meters per second. So this is how to solve velocity questions in ray optics. Now we will discuss in refraction through plane surface a very important topic. You can say an optical instrument, that is prism. What exactly is prism? Let's see. Prism is closed refracting surface having all the surfaces as the plane surface. But you would say glass slab is also like this, glass slab is also like this. But there is a little difference. In glass slab, the deviation could be 0 as the incident and finally emergent rays are parallel to each other. But in prism, deviation is not 0. Okay? Now see what shape of prism we have. Like suppose the very simple prism that you must know is the equilateral prism. This is one of the prism. The next prism you can see is this. This is also a prism. You can see this is a closed refracting surface and all the surfaces are the plane surface. Or I can draw one more shape for you, is this. This is also a prism. So I would like to suggest, when it comes about prism, the picture comes in our mind is the equilateral one. It is the prism, but it is not only the prism. So prism are the closed refracting surface, okay? All surfaces are plane. Now in prism, in almost every formula, what you would find is the prism angle that actually characterizes the prism. So what exactly is prism angle? That we will see angle between the incident and the emergent surfaces. Not incident and emergent rays, we are talking about incident and emergent surfaces. And let me tell you, prism angle in a prism might lie outside the prism also. Let's see. Suppose the first prism is this. The ray is like this, going like this, going like this. So this is the incident surface, this is the emergent surface. Obviously angle between this is the prism angle, that is A. Fine. In second diagram, suppose this is the incident surface and light refracted from here, and this is the emergent surface. So between these two surfaces you can see the angle is 90 degree. So what is the prism angle? Prism angle is 90 degree, and moreover this 90 degree does not lie inside the prism, this lies outside the prism. In the third diagram also you can see, suppose light is being incident on this, going here and finally emerging. So this is the incident, this is the emergent. So ray is going like this. This ray is going like this. Now surfaces are going like this. We are just producing the surfaces, and these are apparently meeting. So this is the prism angle, and again you can see prism angle is lying outside the prism. So prism angle is angle between the surface on which light is being incident and light being emergent, and it is not necessary that prism angle lies inside the prism. Now we have done with the definition of prism. Now we will see the question topic. In prism there are three important question topics. First, you have to be very aware of the all kind of deviations that is being produced inside the prism. When I say all kind of deviations, from this I mean the first is called the paraxial deviation. What is this? Paraxial. When I say paraxial, obviously what I am talking about are the small angles. And when the angle is small, when the prism angle is small, when the incidence angle is small, when the refraction emergent angles are small. The second type of deviation is obviously the minimum deviation. Minimum deviation. And the third one is, what is this? Maximum deviation. Maximum deviation. So this is the first problem topic on prism. After that, obviously there are deviation, dispersion, splitting of light rays, dispersion without deviation, deviation without dispersion, and the next category that we have already done in TIR was the TIR through prism. So these are the basic three topics that we are going to discuss one by one. Let's discuss the deviation types now. Paraxial deviation. Paraxial means the angles are very small. The four angles you can see, I, R1, R2 and E, and the actual formula for deviation is I plus E minus A. A is R1 plus R2. So all the deviation, all the angles here are very small. In that case, deviation is denoted by mu minus 1 into A. But let me tell you, this is not the real formula for deviation. You can use this formula when the prism angles are very small, up to 5 to 10 degree. Obviously, rest of the angles must be smaller as well. The next is the minimum deviation, a very, very important topic for NEET. Minimum deviation. Conditions are angle I is equal to angle E. So angle I and angle E are equal. Hence, the ray are obviously you can see ray are symmetric. R1, R2, the inner angle, these must be equal as well. And when these are equal, you can see the ray inside the prism is parallel to the base. ray inside the prism is parallel to the base. How to numerically define? Mu is equal to sine A plus minimum deviation divided by 2 divided by sine A by 2. This formula we use to calculate the minimum deviation inside the prism. And graphically, if you will define this, see, this is the deviation, this is the incidence angle, and you can see at I equal to E, the deviation is what? The deviation is minimum. One very interesting thing about this deviation is, if you will see this formula, I plus E minus A. So if you are interchanging the numerical value of I and E, deviation remains unchanged. So if suppose I is 15 and E is 30, reversibly I is 30 and E is 15, then also the same deviations. That means in general in Prism the deviations are there for two set of incidence angles, but only unique deviation is the minimum deviation which takes place when I is equal to E. Moreover, you can see the deviation graph is not symmetric to I equal to E. Although the deviations are there for I1 and I2, one deviation is there for I1 also, the same deviation is there for I2 also. But this deviation, the graph is not symmetric about I equal to E, so this difference is not equal to that difference.